Hello and welcome to lesson 2.6, anti-differentiation by substitution. So as we've seen so far, the antiderivatives are directly linked to integrals and how to solve them. So today we're going to talk about actually using a different method to solve some of these integrals. So first thing to note is if you have a family of antiderivatives, where you're not actually looking at the bounds of the expression, but just need the antiderivative, we usually use just a plain integral without any bounds on the function f of x dx. These are called indefinite integrals. And that means that if capital F prime of x is equal to lowercase f of x, then the integral of lowercase f of x dx is equal to the capital F of x plus c for some constant c, where c is some real number. So with this information, as you probably have already started to notice, that some of the antiderivatives, you start to realize if you know derivatives very well, you can figure out the antiderivative. So let's look at some basic antiderivatives and indefinite integrals. So again, I think we've seen this before. Value k is a multiple of the expression f of x dx, where k is some real number. All you can do is just simply factor it out, and you don't have to work with that piece out in that. Also, if you have two functions that are added or subtracted, you can separate them into two functions and find the integrals of each one separately. The next bunch that we're going to see is just some basic antiderivatives that many people just memorize or remember due to the fact that they know derivatives very well. So this one, first one, is kind of like the power rule backwards. Next one is how to find the antiderivative of just 1 over a variable using a natural logarithm. The next bunch are antiderivatives of sinusoidal functions or trigonometric functions. So we have sine, we have negative cosine, we have tangent, we have negative cotangent, we have secant, and we have negative cosecant. So again, most people remember these or memorize these. Next, we have the antiderivative of the natural exponential function and the antiderivative of just a regular exponential function. These next two are not commonly used, so many people just memorize these formulas that you see right here, but you can use them if you need to. And these last two are more commonly used than the other inverse trigonometric functions. So usually just tan inverse and sine inverse. Remember how the rest of them relate to these two, and hopefully you can work from there. So let's do some calculations. Let's do some practice. So, our first problem looks just like x to the exponent negative 2. So that just looks like a regular power. So you've got to work backwards. Remember, the exponent x to the negative 1 would give you, if you found the derivative of this would give you x to the negative 2. But if you multiply this by negative 1, you'd get a value of negative. So you're going to have to get rid of that. So you're going to have to put a negative 1 in front to get rid of that negative. And then add c. Don't forget the adding of c every time. Usually from here, you just simplify. So this will be negative 1 over x plus c. Okay, this next one. Notice the t squared in the denominator. Not necessarily the plus 1 part. The t squared part is what's of help. But the fact that it's being added to 1 is another instance. Well, if you remember, this is actually the inverse of the tan inverse of t plus c. It's right above there, just in a different letter. Okay. Last one for this example. Well, this denominator right here just has a u to the exponent of 1 plus 1. So the only way that's going to happen is if you have the antiderivative as natural logarithm of u plus 1. Don't forget to put the absolute value signs. And plus c. And there we go. Now some of these aren't as easy, so we're going to go over some more difficult ones in just a little bit. So it also matters what kind of variable you're integrating with respect to. So this kind of problem I have here, we have f of x is equal to the function x squared plus 2, and the function u is equal to x cubed. And what we're going to do is we're going to find all these, we're going to calculate all these integrals that we see here in terms of x. So our first one, what I'm going to do is I'm going to write the integral, because f of x is just the function x squared plus 2. I'm going to write the x squared plus 2 there, and then with respect to x. Now since these two variables match, x squared and dx, so I can find the antiderivative of this. Now the antiderivative of x squared is just 1/3 x cubed, and the antiderivative of 2 is just 2x. Again, don't forget the plus c part. Now as this is already in terms of x, we're done. Okay, let's try this next one. F of u is, well, f of u would be the function u squared plus 2. And again, we're integrating with respect to u, so du. So this would turn out to be, again, 1/3 u cubed plus 2u plus c. Now the only issue is we've got this expression, but it's not in terms of x, so we have to change it in terms of x. And here we notice that u is equal to x cubed. So what I'm going to do is I'm going to replace x cubed for every time I say a u. And now I'm simplifying. So here you can see that these two answers for part A and part B are completely different. Related, similar, but not the same. Okay, so let's take a look at our last problem. Now our last problem has the integral of f of u dx. So first of all, I'm going to write what f of u is, which is u squared plus 2. But this is dx. Well, I can't integrate this with respect to x because there is no x. So I have to replace the u first. So put a u cubed squared plus 2 dx. Oh, my apologies. Should it be actually x cubed? Okay, first simplify. Easier to work out. Always simplify. Much easier to work out. And then what we can do from there is we can find the antiderivative, which is just 1/7 x to the 7 plus 2x, again, plus c. And as you can see, based on all these three questions, they're completely different answers. Okay, so moving right along. So let's start looking at problems that are a little bit more complex. So consider the integral 2x times the square root of 1 plus x squared dx. So we want to find the antiderivative of this. Well, readily, there is no known antiderivative that we can use here. But what we can do is we can use something called substitution to help us out. So to use substitution, what you do is you look for something inside the function that has a derivative that's also inside the function. So notice if I let u equal 1 plus x squared, and here's where the substitution of the letter u comes in with in terms of what's in terms of x squared, like what we talked earlier. If you find the derivative of this u, you get the derivative 2x dx. So you'll notice and I'm going to circle the 2x and the dx in there, and you'll notice this piece right here, the 1 plus x squared, is what was originally u. So here's where we're going to go. Show you how we do this. So I'm rewriting my integral originally, and what we're going to do is we're going to substitute. We're going to change the 2x dx to du, and we're just going to change the 1 plus x squared to the square root of u. This, we can work out the antiderivative easier, because this is just u to the half du. So the antiderivative of that, well, the exponent would have been 3 over 2, but I don't have a 3 over 2 in my integral, so I must have multiplied by 2/3 plus c. Now at this point in time, you can also substitute back in the value of x if you want it in terms of x. And there you go. Again, usually they like root symbols, so we're going to change this into a square root of 1 plus x squared cubed plus c. And then you can try finding the derivative of this and verify that it's the same expression that you get in your integral. Okay, so let's try some examples of using substitution to help us out. Okay, this first problem. Let's take a look at this first one. Well, what I can notice is if I let u equal x to the 4 plus 2, I know its derivative is 4x cubed dx. I do notice an x cubed dx in my expression. The 4, not a big deal. So what I can do is actually I can rewrite the 1/4 du as x cubed dx. So now I go back and I'm going to replace what I have. So now I'm replacing x cubed dx by 1/4 du. I'm going to place it right here. And then I replace the x to the 4 plus 2 by cosine u. Well, I can take out the 1/4. The antiderivative of cosine is just sine u. And again, don't forget the plus c. Once you have this new expression, make sure you replace the u back as x, or in terms of x. And there you go. There's your antiderivative. Again, these antiderivatives are just helpful to find out the values for the integrals. Okay, this next one's a little bit more complex. So first of all, please remember secant of the exponent 4x can be written as secant squared x times secant squared x. Now you're probably thinking to yourself, why does this matter? Well, please remember tan squared x plus 1 is also equal to secant squared x. This is our identity that we've seen before. So I'm going to replace one of these secant squareds, just one of them, not both of them, by 1 plus tan squared x. Again, you're probably asking, why would I do this? Well, remember, if I let the function u equal tan x, I know the derivative of tan x. The derivative of tan x is secant squared x. And I do have a secant squared x in there. So now I'm going to change my expression. I replace the secant squared x dx by du, and I replace the tan x by the function u. So this is 1 plus u squared. The antiderivative of this is just u plus 1/3 u cubed, again plus c, and I can now put the tan x back in. So 1/3 tan cubed x plus tan x plus c. And there we go. Okay. Now let's take a look at our last problem. And the last problem actually has us evaluate here. So I'll show you how to deal with an evaluation instead. So in this case, notice the function 4 plus 3 sine x is under a square root. So what I'm going to do is I'm going to let u equal this 4 plus 3 sine x, because I know the derivative of this is 3 cosine x with respect to x. And again, I can notice the cos x dx in my expression. So I'm going to write this as 1/3 du first, is equal to cos x dx. And now I'm going to change this integral. I'm not going to write the bounds yet, because the bounds have actually changed. I'm going to show you how this changes. So the cos x dx is just getting replaced by 1/3 du, and the 4 plus 3 sine x is being replaced by u. Okay, now we should write in the bounds, so let's work the bounds out. So remember, in our expression u, 4 plus 3 sine x, and x takes on two different values. So first find out 4 plus 3 sine of pi over 2, and 4 plus 3 sine of pi. Well, sine of pi over 2 is just 1, so this is going to be 4 plus 3, which is 7. Sine of pi is 0, so this is just going to be 4. So you're going to place these in the exact same spots that they were before. So this is now 4 to 7, or 7 to 4. And please don't make sure you change the order of these. Keep the order the same. Okay, so let's continue to simplify this. I'm going to take the 1/3 out. Going to calculate the integral from 7 to 4. I'm going to write this as u to the negative 1/2 du. Okay, so the antiderivative of u to the negative 1/2 is u to the 1/2, but I must multiply by 2. Don't forget I still have to divide by the 3 there. This is our antiderivative. I'm not going to put the plus c this time because now I have it on specific bounds. So I'm going to put 7 to 4. Now, here is the fun part. You do not need to change this back into terms of x. If you do change it back into terms of x, you're just going to have to change the bounds again. So, what you could do from this point is just substitute the value 4 and 7 in. So this is going to be 2/3 times the square root of 4 minus 2/3 times the square root of 7. Or if you wish, in factored form, 2/3 of square root 4 minus square root 7. Or, because square root 4 can be actually worked out, 2/3 of 2 minus square root 7. Now if you do change back to signs, that's fine, you can, and then just substitute the value in, you're going to find the exact same result. So this concludes this lesson.